In this system, we're dealing with a rigid bar that has a length of L1 from its left side to its pivot point, a length of L2 from the pivot point to the extreme right side, and we're looking for a transfer function that's going to tell us how the vertical position of the right side of this bar is our output and affected by the input of the force on the extreme left. And we're going to see that even though this is seemingly a very simple system, because we're now dealing with a rigid bar rather than just discrete elements like in previous examples, it's actually going to be a little bit trickier to do the modeling and come up with this transfer function. Now, we want to pay attention in what we are to assume in this problem as it's going to come into play in our modeling step. So we are going to assume that the bar is, or the lever is rigid and massless, but it does have a mass moment of inertia J about its pivot point P. And we are going to assume that x, that vertical displacement of the extreme right, is small, which is going to allow us to use small angle approximation. And we'll see how that comes into play as we put together our free body diagram and the relationship between our, in this case, multiple degrees of freedom. So I'm going to start by, I just want to modify this to lowercase f just so that we're dealing with lowercase for functions of time, and that way we know when we do a Laplace transform, capital F is the Laplace transform of little f. So that way that is going to be consistent. Okay, so we want to find ultimately the transfer function I'll call g of x, the vertical displacement of the extreme right, to f, that force on the extreme left. So we need to start with a free body diagram. Again, we're not dealing with these discrete point masses like in previous problems. We have this rigid bar, and we'll see rigid bodies a lot more in vibrations, but we'll see in this simple example how we can start to handle them. Now I'm going to take for my free body diagram the rigid bar itself. I'm going to isolate it and see what is going to be affecting it. Now, I'm already told that the extreme right pivot point, that is defined as x positive up. So in equilibrium, the bar is horizontal. So when x is positive, the extreme right point is up. And when x is negative, it's down. And it's going to pivot around this point P. Now, we do want to look at all the forces that are going to act on this bar and all the moments that act on it. It's a rigid body, so we could have moments acting here. And then we want to see what does the inertia look like. So in our left-hand picture, the free body diagram, I will copy that force F, and that has a length of L1 to the pivot point P, and L2 is the length from the pivot point to the extreme right. I am going to have the forces from the spring and the damper, so I'm assuming tension in both of them here. So we want to look at how x affects them. The spring is attached to the ceiling, so that cannot be translated, but the bottom is going to translate by an amount x. So we want to know, should this be positive or negative quantity? So what value of x causes the spring to go into tension here? Well, when x is positive, that is going to put the spring into compression. So a negative x, or when that point goes down in the negative x direction, we'll put it into tension. So this will be negative k times x. Again, think of what the signs should be here. When x is positive, this needs to be a negative quantity as it should be compression, and that's going to be the case. And when x is negative, I should get a positive quantity. I have a negative k times a negative x, and that would be positive. So negative kx is correct here. And then I have the damper. Here at the bottom, it's attached to the floor, so that has zero velocity always. And when our x dot is positive, when that extreme right has a velocity up, that's going to put the damper into tension. So this will be a positive b times x. So the spring is going to be negative kx, the displacement, and this is actually a bx dot because it's dependent on velocity. So a positive bx dot pointing down, that is when b, the damper, is in tension. So both of those are dependent on this dependent variable x, and then I'm also going to have at that pivot point some reaction. So I'll call this Py, and I will call this Px. And those also can change in time. These reactions are going to be dependent on what the spring force is and what the force in the damper is. Now, those are all the forces that are acting on the bar. Now we can go over to the inertia, and this will get a little bit different than what we saw before. Now, the bar itself, because it's a rigid body, it can translate and it could rotate. So potentially, let's say it could translate vertically. That would be a possible inertia here. In the instructions, we're not told where the center of mass is because that's what we would be tracking, is what is the acceleration of the center of mass times the mass itself. But it's going to turn out not to matter for translation where the center of mass is or what its acceleration is, because we're told to treat the lever as massless. So the translation of the center of mass doesn't matter in the horizontal direction or the vertical direction because there'll be no inertia. So that's why we're going to be able to ignore that the linear accelerations and the linear inertias. However, the bar can rotate around its pivot point at P. So I'm going to, for rotations, we're going to have some angle of rotation here that I am going to define as theta. So this is going to be our coordinate. So actually I'll put the coordinate out here of how we're defining it. So I'm at the moment arbitrarily going to say that theta is positive counterclockwise. And why is that important? It's important because this inertia is going to be j times the angular acceleration, which is theta double dot. So we have this rotational inertia, j theta double dot, that is analogous to when we have those linear inertias of mx double dot. But here, it's an angle of theta, and then the second derivative of it for its angular acceleration. So we have a problem at the moment. Well, what could be a problem at the moment, we have x and we have thetas in here, but we're going to see that actually they are going to be related to each other, and we have to recognize that in order to get the correct equation of motion. So actually, I need to make another free body diagram, or another diagram here. I want to see what happens to this bar as it moves. So I'm going to have the bar in its equilibrium position, which is denoted by this dashed line or dotted line, and then the solid line in this picture is the bar in what I'll call a perturbed position. And why am I doing this? I'm doing this because there's a relationship between x and theta. They are not independent of each other. I cannot change one without changing the other one, and if I know one, I automatically will know the other. That's different than what we saw in other multi-degree of freedom systems where we had independent degrees of freedom. We could hold one, let's say at 0, and move the other one, and the system could still be in motion. This is not the case. I can't hold x at 0 and change the value of theta. Because if I measure this, if this goes up by an amount x, it's going to rotate by an amount theta. And actually, in making this diagram, I am using that small angle approximation that we were told to use when we say assume the displacement of x of t is small. What that small angle approximation lets us say is that from the equilibrium point, let's say this point here, for the small angle approximation says it is going to move only tangentially from its initial position. So that point moves tangent from its initial position, so it would move purely vertically up by an amount x. Now, using this right triangle, I can relate the angle theta to x, because the tangent of theta is going to be opposite over adjacent, so x over L2. Now, this right triangle is coming from the small angle approximation, which again says that these points will move only tangentially from their initial position. For large angles, then we really do have to compensate for that arc that they're going to be going through. So that is why I'm able to write this relationship, but actually that small angle approximation lets me do something else to further simplify this. I have this tangent of theta here. For small values of theta, now we're going to be measuring in radians. For small values of theta, the tangent of theta is approximately equal to theta. I'll write that up here. So tangent of theta is approximately theta for theta small. So I'll just say much less than 1. But that's going to be very small values of theta. We can say the tangent of theta is approximately theta. So that is how I am able to go from the tangent of theta to theta here. And this is going to keep the problem as a linear problem. We're not going to have a trig identity in our equation of motion. Now, I'm making this simplification here, this small angle approximation, because it's going to introduce only a small amount of error as long as that assumption or that limitation of the small angle of rotation holds up, which by rule of thumb is a theta value less than about 5 degrees gives us a reasonable approximation using small angle approximation. If this is rotating more than 5 degrees, these simplifications are going to introduce a lot of error into our problem, and we should solve it using the nonlinear relationship. But for here and for this course where we're keeping things linear, this approximation will be okay for small angles of rotation. So we'll work this in as we get into the equation of motion step then. All right, so let's look at our equation of motion that comes out of this free body diagram. Now, I can actually get a couple of equations of motion out of this because it's a rigid body. So there can be vertical, there can be horizontal translation, and we can have rotation. So I'll start actually in the horizontal direction. I haven't defined that yet. I guess I'll call it maybe Z, just so I have something to mark it here. So if I sum forces in the Z direction, in the left picture, I have P sub X. Remember, P is a function of time, or can be a function of time, that reaction force. And on the right-hand side, well, it's inertialess, so it's always 0 in this problem. In the, I guess I'll call it the X direction here, the vertical direction, on the left-hand side, I am going to have this negative F, since X is positive up, plus a PY. Also up is negative kx, and then down negative bx dot. And that will equal 0. Now this is going to turn out, I can solve for py, I can solve for what that force is, that reaction force. It's going to turn out I don't need to in this problem though. So this equation is still correct. It's going to relate the input force to the reaction force, the vertical reaction force at y, but we don't actually need it to solve it, as we'll see when we start to count up our equations. Because we can also get a moment equation. I'm going to take the moment around p. Right, so on the left-hand side, counterclockwise positive, I am going to have this F times L1. That's the moment that the input force has around that pivot point P. Px and Py will not appear in this equation at all. And then according to my picture, this arrow for Kx is up, so it should be a positive moment, but the force is negative Kx and the distance is L2. Then minus, because I have a downward arrow for the damper, Bx dot times its moment arm length of L2. So that's the sum of, well, moments or torques. Now the right-hand side, though, is non-zero. I have a J theta double dot on the right-hand side. And I'm going to call this equation 1. I'm not going to label the other two because I'm not going to use them for this problem, but I could use that sum of forces in the x direction if I wanted to, if I needed to find py. We'll see, though, when we count up outputs, inputs, and equations, we can get away in this problem without finding it. Now, I could count outputs x and theta, but as I showed above, x and theta are not independent degrees of freedom. In the other multi-degree of freedom systems, they were independent. What I need to do is express it in terms of one or the other. Well, I'm going to express in terms of x because in the find, I want x over f. So I want to get rid of this theta here. So 1a, I'm going to rewrite this now. I have this FL1 minus KXL2. I'll put the x at the back here. So I have a KL2x minus, and I'll put the x dot at the back here as well, equals, now this theta will get replaced. I can take two time derivatives here. I'll show the step there. And I will get x double dot over L2. Because L2 is a constant, the first and the second derivative are going to look like this. I would have theta dot equals x dot over L2, and here I have theta double dot equals x double dot over L2. If L were not constant, if that length could change in time, then I would need to use the quotient rule and it would get more complicated. But because L2 is a constant, the relationship between the angular position and that translational position is the same as the angular acceleration and the translational acceleration. So I can make this substitution of j over L2 x double dot in 1a. And this becomes, again, coming from that moment equation, but with substituting the relationship between the angular position or the angular acceleration and that vertical acceleration. Okay, so I can take 1a and I'm going to do a Laplace transform. So little f is a function of time. That is our input. So that will go to capital F times L1 minus k is constant, L2 is constant. X is going to go to big X when I take its Laplace transform, minus b and L2 are constant. X dot will go to s times x. Here, once again, we're starting at equilibrium, so those initial conditions all drop out. So that leaves us just with this sx from the x dot equals j over L2 s squared times x. And same idea here, zero initial conditions, so x double dot just goes to s squared x. And we'll look at 1b, since that's the only equation so far that I've taken into the frequency domain, and look at my outputs and my inputs, and to see if I have enough to get where I need to go. Right, my input is f, my output is x, so notice 1b, the only output dependent variable is x. That px, py doesn't appear in here. And I have only my one input f. And what I want is the transfer function x over f. So with 1b alone, I have what I need for this problem. If I wanted another transfer function, py over f, then I would want to do the Laplace transform of that sum of forces in the x direction equation, but I don't need it for this problem. That's why I'm not going to pursue it. I have enough with 1b to get the transfer function that I desire. I'll do this one by hand because it's only one equation for one output. So I have here a jl squared s squared x, and I'm going to move these x terms over to the right-hand side, and I'm flipping it like I've done before. So plus bl2 sx plus a kl2x equals FL1. On the left-hand side, I have only these x terms, so I can factor out an x. And what I'm going to do, I don't have to do this, but it'll look a little bit cleaner. I'm going to multiply both sides by L2 at this point, just so I don't have an L2 in the denominator. Because L2 is a constant, it is fine to leave it in the denominator. I never want s's in a denominator in the end, but constants would be okay. But I'll clear this out. So the first term, I have j over L2, so this whole thing is being multiplied by L2, and so is the right-hand side. So I'm left with just a js squared plus a bl2 squared s plus a kl2 squared. And again, the x came out, equals FL1 L2. Where do I need to go? I want x over f. That is my transfer function, and I'm calling that g. So to do that, I'm dividing, well, both sides by f, and both sides by that coefficient, multiplying my x on the left-hand side. So I'll be left with an L1, L2 over js squared plus bl2 squared s plus kl2 squared. And that is, well, one way to express my transfer function. Again, I could have left an L2 in the denominator and had a j over L2s squared, and that would be perfectly fine for this. but this got rid of all of those fractions within fractions that we would have had to look at. So as a quick recap here, how did we get to our transfer function? Well, this turns out to actually be a single degree of freedom system, although we had 2 degrees of freedom that were dependent on each other that we originally wrote it in. We had to then get it down to just 1 independent degree of freedom. But I took my rigid bar here and drew its free body diagram. I put all the forces and moments that were acting on it. In this case, only forces were. And on the right-hand side, my inertias, because it was massless, there were no translational inertias. That is to say, no mx double dot terms or mz double dot terms, because that m is negligible. It's 0. If it were not massless, we might have to compensate for those unless the center of mass were at the pivot point. But that's for a different discussion. But it is not inertialess, so we do have to compensate for the rotational inertia, which will be the mass moment of inertia times its angular acceleration, which I denoted the angular position as theta, so its angular acceleration was theta double dot. But because the 2 degrees of freedom, at least x and theta, were not independent of each other, if I know one, I automatically know the other, and I can relate them using a small angle approximation. So this rigid bar's length does not change, and while it rotates a small angle, I can approximate the movement of any point as purely vertical in this case. If it starts horizontal, it only moves tangent to its original orientation. So that lets me use a right triangle trigonometry here to relate the tangent of theta to the opposite x over adjacent L2. The small angle approximation let me approximate tangent of theta as being equal to or approximately equal to theta, which kept everything linear when I do this substitution for theta and x later. All right, coming down to my equations of motion based on my free body diagrams, I can sum forces in what I'm calling the horizontal direction z and the vertical direction x. In the z direction, it just tells me that horizontal force is always 0. And in the vertical direction, it gives me a relationship between the vertical reaction force Py and the other forces in the system. For this problem, I don't care about Py or solving what it is in time, so this is a true equation. I'm just not going to use it any further. But I do need this moment equation because I do want the relationship between x and F, that input force. And I can get that directly from the moment around the pivot point P. So I have the moment caused by each of the 3 forces that don't act through P. And on the right-hand side, I have that rotational inertia, that J theta double dot. I can make that substitution that I use with the small angle approximation here to substitute in x double dot over L2 for theta double dot. Then we can proceed like we normally do with getting transfer functions. I take the Laplace transform. I identify from this now 1 equation I've made so far, I have 1 output x and 1 input f. This is solvable, and it will get me the transfer function I want, x over f. So with some algebra, I can rearrange this, and I can solve for x over f and get the full transfer function for this system.